Welcome to Chapter 15 of Introduction to Oceanography, Uses and Abuses of the Ocean. So in this chapter, we're going to talk about the different types of uses that we have for the ocean, whether it's physical uses or biological uses. And then we're going to talk a little bit about the abuses of the ocean, and that will lead us naturally into subjects of sea level rise and climate change and why that may or may not be happening.
So we will start with the changes that have gone on the globe, and the primary change has been humans' expansion and our consumption of resources. And a primary factor of this chapter is the fact that we have used more natural resources since just 1955 than all of recorded human history up to that time. So what types of resources are we talking about from the ocean? Well, we're talking about physical resources, marine energy resources, biological resources, and non-extractive resources. And those four resources are all known as the marine resources. So your physical resources result from the deposition of or precipitation or accumulation of useful substances in the ocean or on the seabed, and that could be calcium carbonate, that could be manganese, that could be gold or silver, that can be salt. Lots of different physical resources come from the ocean. Diamonds. Marine energy resources result from the extraction of energy directly from the heat or the motion of ocean water. So there's geothermal energy that can be extracted, or we can create energy using the motion of ocean water. Biological resources, of course, are your living animals and plants collected for human use and animal feed. And then there are the non-extracted resources. Those non-extracted resources, uses of the ocean in place, right there where the ocean is, transportation of people and commodities by sea, recreation, but also kind of the seedier side, a non-extractive use of waste disposal. Now, our marine resources can be classified into either renewable or non-renewable resources. So those are our two types of marine resources. Renewable, of course, naturally replaced by the growth of marine organisms or by natural physical processes. And then your non-renewable resources present in the ocean in fixed amounts, and they cannot be replenished over short time spans. Certainly over hundreds of thousands or millions, tens or hundreds of millions of years, oil and gas and other solid mineral deposits can be replenished, but in our lifetimes, in those short geologic time spans, those types of non-renewable resources simply cannot be replaced. So what are the physical resources from the ocean, whether they're renewable or non-renewable? You have petroleum and natural gas. Some 34% of crude oil and 30% of natural gas actually comes from the seabed. And as you saw in the book, in the illustration in the book, figure 15.3, oil and gas are not necessarily found in big hollow reservoirs, big lakes of oil or big pockets of gas, but they're actually within the pore spaces of a rock. Think about a sponge and all the little pore spaces in a sponge. If that sponge is soaked in water, that would be the oil, the natural gas, and it's the pressure of the natural gas and then the combination of the weight of overlying rock that drives oil or natural gas through those porous rocks towards drills. And so one of the physical resources of the ocean, petroleum and natural gas. Minerals can be recovered by deep sea mining: copper, gold, lead, zinc, rare earth elements, very special elements that can be used in things like cell phones. So lots and lots of different minerals, and perhaps most of the commercially necessary minerals that we find on land also can be found with deep sea mining. Believe it or not, just sand and gravel from the ocean used for construction, 1.7 billion tons annually. And then in addition to that, there's all types of other sands that are created by the ocean that are rich in calcium or different other elements that are also mined for use, and whether in construction or other types of production. We also get what are known as evaporites from the ocean, salts. So when we talk about salt in a salty ocean and the salt water of the ocean, we're not talking about salt like table salt, although that's one of them. The salts are all those other elements that if you evaporate the ocean are left behind. Calcium carbonate, gypsum, and table salt are just a couple of the main ones, actually. And of course, table salt, calcium chloride makes up the vast amount of it. That's why the water tastes salty. And then, of course, Fresh water is a physical resource from the ocean. Fresh water from desalinization, whether it's through distillation, boiling, freezing, or reverse osmosis. And as we read in the book, all of these processes are very, very expensive. So our fresh water needs across the world can't simply be met through desalinization. It's going to be very, very expensive. And we also learned in the book that fresh water is the ultimate limiting factor in terms of how many people can live in any area. There has to be enough fresh water for all those people to drink. From the physical resources of the ocean, we'll turn to the marine energy resources. How can we get energy from the ocean? We can get it from windmills, or we can get ocean energy to generate power. So windmills, simply like any windmill, of course, but at the ocean you have these steady winds, these high winds that continuously blow in many areas for very, very long periods of time. Enough persistent and consistent wind that windmills can generate significant energy. And we can also use the energy of the motion from the ocean, whether it's wave motion or currents that move water from one point to the other in the same direction, or tides that move very large amounts of water back and forth. All of that movement of water can be tapped into to generate ocean power. One example of that, of course, is going to be in your wave energy. We can tap into wave energy to generate power.
Atlantic rollers crash into the rocks of Orkney, turbulent waters bursting with raw power. The question being researched here: can we turn this into electricity? Rising from the sea, something that could be from a Bond film. This is the open hydro tide turbine, a marine power station. Picture this as a kind of wind turbine but underwater, harnessing the power of the tides. The waters of the Atlantic surge through here to the North Sea and then back again at nearly 10 miles an hour. This device traps that energy. There's huge potential here, but it's early days. This animation shows how the giant turbine sits on the seabed and spins in the tide. The plan is for dozens of these, the power cabled underwater back to land and plugged into the national grid.
We're a great fan of renewable energies, of all forms of renewable technology, but tidal is one of the only that is predictable. So you predict the tides by the movement of the sun and the moon. That gives a very persuasive argument for investment into the technology.
As the device is lowered, the tide surges past. What no one knows is whether this can be scaled up. This is just one of many ideas being tested. We head out to another side of the Orkney Islands. The swell is building, and there's another weird sight. This is the Oyster, a wave power machine, rearing out of the water. It's a Scottish design, just installed. This is the top of a giant flat, about twice as high as a double-decker bus, and every time it moves back and forth with the waves, it sends a pulse of water under pressure to the shore, and that's used to generate power. Imagine 1,500 of these. In theory, they generate the electricity of a conventional power station. Can you really imagine this generating useful amounts of power?
Oh yes, totally. I mean, I wouldn't be here if I didn't believe that there was huge potential. This is a sustainable energy resource, and we just have to make the most of capturing the energy from it.
But none of this is easy. This wave machine, Pelamis, suffered mechanical problems. Its makers are bouncing back with a bigger version. At the moment, Britain does have the lead in marine power.
There is huge potential, absolutely huge amounts of energy out there. And in fact, we don't exactly know how much, but it is epic. But there is an absolute risk that we could fail to actually develop the technology that gets the energy out of the sea. And if we're not careful, we could end up buying this technology back from overseas later on, which simply would be silly.
So the coastlines of our island nation hold great promise for green power from the ocean. The next few years will show if it's possible. David Schuckman, BBC News, Orkney.
All right, in addition to marine energy and physical resources, of course, there are biological resources of the ocean. Marine sources account for about 16% of the total animal protein consumed by human beings. Fish provided more than 1.5 billion people with almost 20% of their average per capita animal protein. That was back in 2007. And in 2009, we registered 580 million pounds of fish consumed each and every day. That is a lot of protein. The fish, of course, crustaceans and mollusks, those are our most valuable living marine resource. And commercial fisheries caught or grew about 140 million metric tons of the stuff in 2008. Since 1972, the world human population has grown, and average per capita world fish catch has fallen significantly. So the population's growing, but the fish catch is not keeping up. So that's going to set us up with a little bit of a problem. Here we have a couple of graphs giving you some information in terms of marine capture fisheries production. So where do we get the most type of a marine bioprotein, and you can see the different lists here, and then the countries that are harvesting the most, with China in the lead and Japan coming in after the USA, and then where are we doing this harvesting? In the Northwest Pacific, the Southeast Pacific, and the Central Pacific, of course the Atlantic and the Eastern Indian Ocean as well. All right, when we talk about fisheries and the amount of fish in the ocean of any different type, we understand that there is a maximum amount that we can take in any given time period, let's just say a year, and that maximum amount is what's known as the maximum sustainable yield, the maximum amount of any species that can be harvested without affecting future yield. So you can take this much each year, every year, and you'll always have that type of fish, that type of mollusk, that type of crustacean. Overfishing, of course, is a status assigned to fish stocks, a type of fish, a type of mollusk, a type of crustacean that have been harvested, so there's not enough breeding stock left for replenishment. You've exceeded your maximum sustainable yield, then you have an overfishing situation.
This is Japanese scientist Shukei Masuma, a leader in tuna research. He is worried because too many tuna fish are being killed. Today, bluefin tuna have become rare. Some people spend hundreds of thousands of dollars for one fish. And on average, the fish they can get are getting smaller. This means that bluefin tuna are being killed before they are old enough to have babies. To help solve this problem, Masuma has been breeding bluefin tuna on his fish farm. Masuma says he is trying hard to learn about the tuna and how to help them. Every evening, Masuma waits at the edge of the breeding pool to see if there are any new tuna eggs. If there are new eggs, Masuma must carefully catch them and move them to small tanks in the main house, where they will be safe and he can take care of them. Here he can watch the tuna grow up and learn more about them. Masuma is afraid that if people don't do something, the groups of tuna in the region may soon be destroyed. His goal is to keep these tiny tuna alive until they are big enough to be returned to the sea. It's a difficult job. Many of the baby tuna in Masuma's farm don't survive to become adults. But after spending years trying, Masuma has found the right combination of food and temperature to keep the baby tuna alive in large numbers. Today, Masuma has a visitor. Talented oceanographer Dr. Sylvia Earle studies ocean wildlife. She is worried about improving the tuna's chances of survival and wants them to be safe in their natural environment. Dr. Earle is very impressed with Masuma's work. She can see that the baby tuna at his farm are healthy. Masuma is the first scientist who is able to grow baby bluefin tuna in a farm. Masuma's work is very inspiring. Someday, these tuna might swim in the wild, and from them may come a completely new population of bluefins. But first, they must survive a variety of dangers, especially human predators. Scientists say the Atlantic bluefin tuna population is now only about 20% of what it was in the 1970s. In the Mediterranean, the species is in great danger as well. And in the Pacific, scientists have been reporting that the bluefin has almost disappeared. But there is hope. Scientists' advice is that we must have stricter rules on the size and number of fish humans can catch each year.
So what you heard was correct. Those bluefin tuna can actually pull in upwards of $100,000 each if they're big enough. And in the northeastern part of the United States, in the western Atlantic, northwestern Atlantic, they'll actually use airplanes to go out and find the tuna, and then the airplane will radio to the boats to go and try and get the tuna. So when we talk about fisheries, we got to get the fish out of the water somehow. Typically, we're going to use very, very large nets. And there is a concept in this that you're not going to just get the fish you want. You're going to get a whole lot of other stuff. And that's referred to as bycatch, animals unintentionally killed when other species are being harvested. And sometimes the bycatch actually exceeds in a tremendous way the actual target catch. And this largely occurs when we talk about bottom trawling. And there's a little bit of a illustration here. There's your little trawler, and you can see how large these nets are, and they trawl across, they drag across the bottom, and they get everything in their way. And this is the type of a catch they bring up, but only a certain amount of that fish, a certain type of that fish is what those fishermen want. So one of the solutions, or two solutions, is aquaculture and mariculture. Aquaculture is growing or farming plants or animals in a water environment under controlled conditions. That scientist with the tuna was doing that when he brought the little baby tunas and the eggs into his laboratory. That would be aquaculture. The marine culture is what he did out in the bay there, farming marine organisms, usually in estuaries or bays or nearshore environments, or in specifically designated structures circulating seawater. The problem with mariculture like this is that when you have a bunch of these fish all in one spot, they create a monoculture. And even if it's in a bay or a fenced-in area, that area is going to have some negative impact from that fish. And even if it's just the waste that those fish produce, it's going to have a negative impact. So there are pros and cons to both of these concepts. All right, from physical to marine energy to biological to now the non-extractive resources, or resources of the ocean that you can't take out of the ocean, and they would include transportation and recreation. So oil accounts for 65% of the total value of the world trade transported by sea. So of everything transported on the ocean, about 65% of that's going to be oil. Then we have iron, coal, and grain. The other type of non-extractive resources that we talk about are ocean liners or cruise ships. And then we also have to consider the value of coastal real estate. If a house on the west side of A1A averages at maybe, let's say, $500,000, but the houses on the east side of A1A average at $1.5 million, then you're looking at a $1 million per home benefit, non-extractive resource of being along the ocean. And that's a resource that has to be considered as well. All right, so what are some of the environmental issues for the ocean? And of course, it's easy to know. We probably all know this. Humans, the biggest problem for the oceans, human demand has exceeded Earth's ability to regenerate resources since about the early 1980s. That's when it's been estimated that the ability for the Earth to regenerate its resources no longer kept up with the human demand. Since 1961, human demand on Earth's organisms and raw materials has more than doubled, and it now exceeds the Earth's natural replenishment capacity. So the ability for the Earth to replenish what's there currently, we're exceeding that by about 20%. And we have been since, again, the 1980s. So one of the human threats is not just what we extract out of the ocean, but what we put back into the ocean in terms of marine pollutions, and there's obviously very many of those. So the introduction of pollutants into the ocean by humans, and that can either be substances or it can actually be heat. Like we have a nuclear plant, we have cooling towers, and we heat up a bunch of water, and then we dump that water, let's say, into the Indian River Lagoon. That hot water is going to have some impact on that area of the lagoon, and likely a negative impact. So it's not just substances, it can be energy, and it changes the quality of the water or affects the physical and biological environment. In the case of warm water from nuclear plants, well, manatees may love that, but it may have a pronounced impact on other biological activity. So pollutants directly or indirectly interfere with the biochemical processes of an organism. There's lots of factors how much pollutant is in the water, what's the toxicity of the pollutant, and how persistent. Is it a pollutant that goes in and biodegrades very quickly, or is it something that will linger for a long time or maybe forever? Because some pollutants are actually biodegradable. So here is a kind of a pie chart of pollutants. As you can see, a big chunk of that's runoff and discharges from land. So when you see the sign by the street at the gutter that says, drains to a lake, that's what it's talking about. Don't put anything in there because it's going to eventually end up on the lake. And of course, at the land, or I should say at the atmosphere-ocean interchange at the surface of the ocean, a tremendous amount of gases go back and forth. And so the airborne emissions that come from land can end up in the oceans. Then you have shipping and accidental spills, just ocean dumping accounting for 10%, and then offshore mining, oil, and gas drilling about 1% of pollution. So during the 1990s, some 1,430 million tons of pollutants in the form of oil entered the world ocean each year. About half this amount was from natural seeps. So what does that mean? Well, oil is in sedimentary rock, and sedimentary rock is not only porous, meaning it has holes and fractures, but it also has permeability, meaning liquids can flow through those fractures and those holes. And so if you have a porous sedimentary rock near the surface and there's oil in it or beneath it, it may seep up into the ocean. So half of this oil really came naturally. Only about 8% from marine transportation, and then other contributions from loading or discharging of oil and flushing oil tankers. And of course, we have two different types of oil. We have crude oil, which is largely biodegradable, and then refined oil, which hangs around for a much, much greater period of time. So when you think of the world's largest oil spills, if you ever watched Waterworld, you may remember the tanker, the super tanker, the Exxon Valdez. Well, the Exxon Valdez was well known for the 11 million gallons of crude oil it dumped into Prince William Sound, but that doesn't even make the top 10 so far, where there was a intentional, back in 1991, dump in the Persian Gulf of 240 million gallons. And of course, we've had in 2010 and in the Gulf of Mexico in 1979. So some data basically on how much oil has been inadvertently or purposely dumped into the ocean over the decades.
For fishermen like Kip Marquise, the spill could not have come at a worse time. This is your one shot at work this season.
That's absolutely correct. Other than this, we have no work.
Since the spill, the fishing industry has been all but shut down here. About 1/4 of the fish harvested in the continental United States come from Gulf Coast waters. Billy Nungesser is the Plaquemines Parish president.
We should have started planning the cleanup while we were still watching that rig burn.
After days of watching Coast Guard and BP ships try and fail to contain the spill, fishermen are frustrated. Waylon Burris is a shrimper.
They bring in a lot of outside people that's never even been here before and don't know the waters as well as we do.
The fishermen are hoping to get hired and paid by BP. They received some training in how to clean up oil spills. Now they're waiting. And they haven't called you?
No.
You haven't heard from them?
No.
Out of more than 100 shrimp boats in this Venice marina, fishermen here say only one has been hired for the cleanup. Attempts to contain the spill are continuing using those bright orange booms. But high winds and waves have washed many of the booms ashore already. The oil is a thin sheen about the thickness of a couple of nickels in some spots. The goal is to skim it off by laying out more booms in a triangular formation. So far, about 1 million gallons have been skimmed off. Aircraft are playing a role too, spraying a chemical used to break up the oil. But the slick is still growing, and there is little reason to be hopeful.
I think this is going to be devastating.
Fisherman Anthony Stepalkovich.
It's probably going to kill all the marsh grasses and stuff. No telling how many little animals are going to really suffer pretty bad.
You know, people worried about the pelicans and what about the children? What about the wives? What about the people? You know, pelicans are nice, but what about people?
All right, so this is a cutaway of an oil slick, and there's a platform, you get an oil spill, you get the slick on the surface, you're going to get some evaporation, photo oxidation, so sunlight is going to remove just a little bit of that. quite a bit of it is going to turn into tar balls, and these tar balls can last for a long time. Dissolution, basically just the dissolving by water, and then sedimentation. So there's a number of different processes. The smaller molecules evaporate or dissolve in the water beneath the slick, but within a couple of days, you start to get these tar balls, and they may persist for months. And then the crude oil itself, it can be consumed by biological activity. Bacteria will eat it eventually, but that refined oil is going to last a whole lot longer. It's much more toxic, and it's going to take a long time for the natural processes to clean that up. So we also have other pollutants, some known as toxic synthetic organic chemicals, and like these and heavy metals both can be biologically amplified by biomagnification. That's essentially an increase in concentration in organisms higher in the food chain. So these toxic synthetic organic chemicals, small amounts of them can cause illness or death. We're talking about chlorinated hydrocarbons, PCBs. Biomagnification is this idea that if a little itty bitty fish consumes a little itty bitty amount of that, and then a slightly larger fish eats a whole bunch of those little itty bitty fish, well, these heavy metals and these chemicals, they're not going to be dissipated, and they're going to all, whatever the fish consumed, the little fish consumed, it's going to be there. So that big fish consumes those little fish, now it has all of theirs, and a slightly larger fish consumes a bunch of the medium-sized fish. That larger fish is going to have all of those chemicals, and then as you go up the food chain, you get an intense magnification of either the toxic synthetic organic compounds or these heavy metals such as mercury, lead, copper, and tin. And that's why there's been real concerns over people who eat too much swordfish, because the swordfish is at the top of the food chain, and they have a lot of these heavy metals in them, because the swordfish eats smaller fish that eat smaller fish that eat smaller fish, and there's biomagnification and increase in concentration in organisms. And it's not just swordfish. Tuna and other large predatory fish have the same type of problem, where they are consuming smaller fish that already have these chemicals or these heavy metals magnified inside them. All right, another waste that is very prevalent in the oceans, maybe even shockingly so, is plastics. And of course, plastics are not going to biodegrade. And from 1960, the generation of plastics compared to the recovery, and when we say recovery of plastics, we're basically saying recycling. So a whole lot of plastic has been produced, 30-some millions of tons per year, and very few tons at all are recycled. And so it all ends up somewhere in landfills or in the world's oceans. And in both the Atlantic Ocean and in the Pacific Ocean, these what are known as gyres, let me go back to that, these gyres, which are where the water turns. So we have the Gulf Stream comes out of the Florida Straits, goes up here, and then the Canary Current comes down on the other side of the Atlantic Ocean. The bottom line is that the ocean current in the Atlantic and the North Atlantic is clockwise, as it is in the North Pacific, and that clockwise turning, Coriolis, or the deflection of objects that are free moving in the ocean or the atmosphere to turn to the right, Coriolis causes those plastics to begin to accumulate in the middle. And this is pieces of plastic per kilometer, per square kilometer. In these orange areas, we're talking 100,000 pieces of plastic in a square kilometer, and they refer to it as the Atlantic garbage patch or the Pacific garbage patch. And this is a person in a boat in that garbage patch. This is out in the middle of the Atlantic Ocean, a region they refer to as the Sargasso Sea, where all of this plastic floating on the surface has accumulated as the winds and the ocean current sort of blow around the Atlantic, and the Coriolis deflects everything to the right, and it just accumulates in this massive garbage patch. And that's literally what it looks like. This is a shockingly visual representation of human pollution on planet Earth, in this case in the ocean. Now, there are additional problems with pollution in terms of just the ick factor and the yuck factor in killing the big fish or biomagnification or the garbage patch. The problem is when you pollute these habitats, you're going to keep the larger animals forever existing, because most marine animals typically start out somewhere in these bays or estuaries. So polluting bays or estuaries can literally cut off the supply of young, whether there's crustaceans or mollusks or fish, to ever make it out into the ocean. And of course, the same threats, pollution from rivers, oil spills, and sewage. And again, when we're talking about bays and estuaries, like the estuary, the Indian River Lagoon, or some of the other lagoons here in Central Florida, we have sewage issues because we have septic tanks, and septic tanks are open underneath, and basically it all sort of leaches down in the soil and makes its way into the water, into the water table, eventually into the estuaries, and then also runoff from fertilization. We put a bunch of phosphorus and a bunch of nitrogen down in our grass to fertilize it, and that all makes it into the bays and rivers and estuaries, and that really has a tremendous impact on polluting and poisoning our bays and rivers. And the Indian River Lagoon and many other areas are really in drastic situation because of that. And then a whole nother problem, as we pump more CO2 into the atmosphere, it's absorbed in the atmosphere. Then again, that ocean-atmosphere interaction, the CO2 is readily absorbed in the ocean. As a matter of fact, a massive amount of the CO2 that we put in the atmosphere since the late 1800s has actually ended up in the top of the Atlantic, and CO2 acidifies the ocean. When you put CO2 into water, you slightly acidify the water, whether it's rainwater or ocean water, and a more acidic ocean is going to be bad for organisms for a number of reasons.
So the oceans had time to adjust to any increase in acidity.
The problem is that today we're pumping out so much carbon dioxide that the ocean just can't keep up.
As a result, they're turning acidic faster than they have for millions of years. The first creatures that will suffer will be the coral that make up the world's great reefs. Their skeletons can't form if the water becomes too acidic. If the oceans continue to acidify at their current rate, coral could eventually disappear from our oceans. With the coral would go all the other life that depends on them.
For ocean acidification, we have a far greater impact than the death of coral reefs. Change in the ocean's chemistry threatens the overall balance of Earth's life support systems. The health of our planet is so intimately connected with the conditions in the sea that these changes may have untold consequences for our world.
If ocean acidification continues, coral would be just the beginning. Phytoplankton are also vulnerable to increasing acidity in the sea. In the long term, this could endanger one of the main sources of oxygen on the planet. But what about the short term? What will these changes in the oceans mean for us? The thing is, the oceans have been stable for millions of years. We are heading into uncharted territory. So we really don't know what the full implications are likely to be. What we do know is that the oceans are fundamental to all life on Earth. Ultimately, the survival of every creature on the planet depends on the oceans remaining healthy.
So ocean acidification is just one more aspect of pollution and the impact on our oceans. Again, they're many faceted and lots to talk about and lots to concern ourselves with, and something you could study greatly in depth in other environmental science courses, or if you chose to study environmental science for a 4-year degree or master's or a doctorate. All right, there are marine protected areas. They do offer some hope. National Marine Protected Areas, NPAs. Miami, I'm in Hawaii. Much of Hawaii, all around Hawaii, is a national marine protected area. Coral Sea, around Australia, British Columbia, Great Barrier Reef. There's lots of them, and the more, of course, we have, the better off we're going to be. We have talked about the greenhouse effect, and we sort of mentioned the fact that extra CO2 is a bad thing and could potentially help to warm the globe. Carbon dioxide, methane, CFBs, and even water vapor essentially absorb the heat given off by the Earth every day. When the sun strikes the Earth, it heats the Earth up. The Earth gives off that heat. That's what warms the atmosphere. And if you had none of these gases, all that heat would just radiate out into space. But with water vapor and carbon dioxide and methane and even nitrous and ozone, those gases actually absorb that heat as it goes out. And the more of those gases we have, and those gases have always fluctuated on planet Earth, but they've been fairly stable for tens of thousands of years perhaps. And the more of those gases we have, mathematical models predict that we will continue to change the climate or perhaps warm the climate. And here's just a quick illustration of the global greenhouse effect. The sun's energy comes in a shortwave radiation. It's a very short energetic radiation, strikes the Earth. Some of it's reflected and scattered, but about half of it actually serves to heat up the Earth, and that's a very shortwave, very energetic radiation that comes in. Well, once the Earth heats up, it emits a longer wave radiation, and that longer wave radiation essentially is heat. And the important difference is the sun's shortwave radiation essentially passes through the atmosphere. It's not absorbed, but that longer wave radiation that comes off the Earth, that infrared radiation, is absorbed by those greenhouse gases. It will be absorbed by those greenhouse gases, whether it's water vapor, carbon dioxide, methane, nitrous, even ozone up in the stratosphere. And if we as humans put way more of that carbon dioxide or methane into the lower atmosphere, the theory, of course, the hypothesis is that we'll continue to warm the lower atmosphere and we'll continue to see some level of global warming. Here are the different tons of carbon or carbon dioxide that are put into the atmosphere each year, and this is what's known as the hockey stick graph, because up to about 1880 it was very, very minimal, burning of maybe coals and whatnot. But then 1880 was the Industrial Revolution, and we began to burn coal and then petroleum and then natural gas eventually, and we began to add cement production in there in the 1950s. And all of these processes, human processes, vastly increase the amount of carbon dioxide in the air. And this is known as the hockey stick graph. And this is that one shocking piece of data that scientists use to show that from 1800 and from many centuries prior, there's almost no change in the amount of CO2 going into the atmosphere. And then very suddenly after the Industrial Revolution, it began to increase dramatically. And again, I mentioned this earlier, the Earth's total heat content is growing. The Earth's getting warmer, but up to now, about 90% of that has been stored in the upper 700 meters of the ocean. So what we've done first is we've certainly heated the land and the atmosphere a little bit, but we've heated the upper layers of the atmosphere of the ocean significantly. And the problem with that is that water, like all substances, will expand when it's warmer. So thermal expansion of the ocean is actually one of the reasons why we see a concern with sea levels coming up, because as we heat full 700 meters, 2,300 feet of the ocean, we heat it up even a few degrees, that thermal expansion, that very minimal expansion of water as it heats up, is going to result in overall a sea level rise. Even if it's minimal in some places, it will have a bigger impact in other places. And then you add to that melting glaciers.
It takes a steady nerve to sail into the Ilulissat ice fjord. These waters on Greenland's west coast are littered with icebergs, some weighing millions of tons. The vast blocks of ice tell a disturbing story. The Greenland ice sheet is in retreat. This is where the icebergs are formed. You can see the steep drop where the ice shears off the glacier front. The Northern Hemisphere's most active glacier has retreated more than 10 miles in a decade, the fastest since records began.
We used to think that ice sheets like the Greenland ice sheet behind us would react on very long time scales. Yeah. But we're seeing reactions not in 100 years, but in 1 to 2 years. So something is really pushing this thing.
The ice melt threatens rising seas and rising temperatures as the planet absorbs more heat. I joined a team of scientists bound for one of the most remote research stations in the world. Their aim to decode the message coming from within the ice. At Camp Neem, the ice is 1.5 miles thick and at bottom hundreds of thousands of years old. They're drilling samples from the oldest ice, which predates the last great warming of the Earth. They're concerned that man-made greenhouse gases have now set off a climatic chain reaction, which will be hard to stop.
A lot will depend on the next few years. We have to act very soon, I think. If we delay it anymore, we're going to find it much harder to mitigate the changes that are already occurring.
This month, the world's environment ministers came to Greenland for talks in the run-up to December's climate change summit. The scientific consensus says industrialized countries must cut greenhouse gas emissions 40% by 2020 to avoid the worst of global warming. Politically, that looks impossible. The search for compromise is on.
You can't build up expectations now and the pressure on politicians and governments worldwide so that they have to act. The whole trick is to make the price so high that they do not dare not to deliver.
The message that is coming from all of the science being done here in the Arctic could not be clearer. The warming effect is dramatic, and it is speeding up. The politicians know it, but they're still arguing about how to respond. The disconnect between the science and the politics is growing.
All right, so some of the factors that go into those models that sort of want to indicate we increase CO2, we're going to increase temperatures, are the increasing amounts of greenhouse gases, gases that come from volcanic eruptions. Believe it or not, sunspot activity can increase the amount of solar radiation that arrives at the Earth's surface. And then that rate of CO2 transfer from the atmosphere to the ocean. For years, some scientists thought that the ocean could just act as a big sink. We could just put all that extra CO2 in the ocean. But we're beginning to see that that's not going to work again because of ocean acidification and thermal expansion. So a mathematical model of climate change, there's 5 factors capable of altering the climate. And then they're all summed up by what has been modeled and what's been observed. So the colored things in the bottom show greenhouse gases, ozone, solar, volcanic, man-made sulfates, different things that may or may not have an impact, whether positively or negatively, on the climate in terms of temperature. And then all added together and modeled, the brown line shows from 1900 to 1990 what those 5 factors, what impact they should have had on the climate, and then we see what has been observed, and we can see where what was modeled and what we've observed largely ties closely together, and this gives some validation, some credibility to these global climate change models that we're basing some of these predictions on. So the solution, of course, is in education and action, and I hope as you wrap up this course, as we're doing now, you'll know that we're all obligated to be informed on these issues that affect the earth, the ocean, the air, and we need to all learn how to weigh the evidence and listen to the arguments and know which arguments are good and which arguments aren't. And probably most importantly, we all need to know that, the actions that we should take or probably need to take need to happen now. And they could be as simple as what you do with a plastic bottle, what you do in terms of fertilization in your own property. Small things that just make you a good steward of planet Earth can help in these more long-term issues. So this is going to wrap up Oceanography, and I want to wish you all well in your future studies and let you know that if you have any questions either now or anytime in the future, please do feel free to email me at any time. And good luck with the rest of your education and your careers as well.